Hi guys, we're back and now we're going to get into the topic of igneous rocks. And igneous rocks, as we hopefully know by now, form from the solidification or the freezing of a melt. So that melt is either a magma, a molten rock material underground, or a lava, which is molten rock that has experienced some kind of degassing and is on the surface of the earth. And so we're going to start out actually talking about magma, the material that eventually forms the igneous rocks, to help us kind of understand how igneous rocks come to be and why they end up having various compositions. So our first topic is about kind of just understanding what magma is and how it forms. Okay, so magma formation. So magma forms as a result of some sort of rock melting, and this can happen at different temperatures. And of course, there are similar temperatures where rock that's getting hotter will melt, and that's a similar temperature that same rock will end up freezing again as it cools down. So same thing with water, right? About 0 degrees Celsius or 32 degrees Fahrenheit. Ice will either melt if it's getting warmer or freeze if it's getting colder. And so there's that same kind of temperature point that can be either thought of as like the melting point or the freezing point of rocks. And it varies depending on which rock we're talking about. And to be more specific, it actually varies by the different minerals within the rocks. So different minerals within a rock might melt and or freeze at different temperatures. And that freezing and melting point is also going to be impacted not only by the temperature, but also by the combination of temperature and pressure. So there's kind of a range of temperatures over which this melting and or freezing happens. And generally it's between about 650 degrees Celsius and then over about 1100 degrees Celsius. And after that temperature, pretty much all rocky materials are going to be melted. So as I already mentioned, magma basically refers to these melts when they're underground below the surface, and then lava is the same molten rocky material that has kind of reached the surface. When it reaches the surface, it's under less pressure, it's usually lost gases, but at that point we consider it lava as opposed to magma. Okay, so we know that heating up is of course something that's going to be required for lava or magma to form. The normal temperatures that we have at the Earth's surface are not hot enough to melt rock, so it's going to be melting underground where the Earth is hotter. So we talked about this idea before about the geothermal gradient, where when we go from the surface of the Earth up at the crust through the lithosphere, asthenosphere, mesosphere, outer core, inner core, we're going to be encountering areas of warmer and warmer temperatures. So that's referred to as the geothermal gradient. And the reason that there's this heat and this energy and these high temperatures down within the Earth has to do with the way that the Earth was formed. So at the beginning of the class, we talked about the fact that there was the collisions between all these much smaller particles of mass that happened kind of in the space where the Earth is currently orbiting, and all that material that had individual kind of kinetic energy as it was moving around in space is kind of gathered in the mass that is Earth today. So a lot of that kinetic energy that the individual pieces had as they was moving around is still within the Earth. The Earth has been cooling over time. Of course, the surface of the Earth is cooler than the core of the Earth because it's able to lose heat more effectively to the cooler atmosphere and space, where the inside of the Earth is much more insulated from that energy loss. But there's another process of radioactive decay of certain materials that also releases energy. So some of the materials that naturally occur within the Earth experience a radioactive decay process that we're going to talk more about later in the semester, but that is a process that releases energy. And so we're not exclusively just losing the energy that we had in the early Earth over time. We're losing some of that energy, but then we're also gaining some energy back or transforming the energy to contribute to temperature maintenance through this radioactive decay process. So the core of the Earth, we now think is about 6,000 degrees Celsius. That's actually warmer than we thought it was about a decade ago. So another example of why science is changing, and we're improving our knowledge all the time through new information. So of course, if you're all the way down at the Earth's surface, it would be hot enough for all these rocky materials to melt. However, you may remember that the Earth's core itself is actually not molten. We know that it's solid based on the patterns of S waves and P waves moving through the Earth. And that's because there's so much pressure down there that the pressure is able to force the materials into kind of a rigid solid state by holding them in formation due to pressure. So as I mentioned before, pressure is a factor as well as temperature in determining what is going to be melted and not melted. Okay, so near the surface, as we go down from the surface of the Earth, we know that the temperature of the Earth increases according to this geothermal gradient. It doesn't happen in a linear fashion, meaning we don't have the steady progression of the exact same amount of warming with each increase in depth. That's the same increase in depth. So you can see that this line that's showing an increase in temperature going down from the surface isn't straight. At first, there's a more shallow drop off in temperature, and then it gets steeper, and then it gets less shallow. So as we encounter these different layers of different density and made up of different materials. And you can see that in this region up here, the geothermal gradient is losing about 20 degrees or 30 degrees, it's increasing by about 20 degrees or 30 degrees per kilometer in depth within the crustal region of the Earth, which is the region that's shown up here. And so that steady increase in temperature warms up the Earth quite a bit, but doesn't, within the depth of the crust that can be fairly shallow, doesn't bring the rock up to a temperature that's adequate to melt it. So just by going 5 kilometers down below the Earth, you're going to get hotter. You might get up to 100 degrees Celsius, 150 degrees Celsius, getting down 20 kilometers more, and so on and so forth. But you're not actually going to be getting up to a temperature that in and of itself would create melting. So this is a really important point. Where we do find magma forming in the vicinity of the Earth's crust, there's always some additional factor that is contributing to the melt. It's not just the condition where anywhere on the Earth where we dig down 50 kilometers or 100 kilometers below the surface that we're going to find molten rock. That's not the typical condition that we find. We find it in these areas that are below the surface that are, yes, warmer, but then there's always some additional factor that's contributing to the melting of the rock besides just the increase in temperature. Okay, so we're going to kind of go through those different things that could happen that could contribute to the melting of rock to create magma. And the first one we mentioned before in the context of plate tectonics, and this is the role of volatiles. So remember that volatiles, V-O-L-A-T-I-L-E-S, are these compounds that can exist in a gaseous form at the conditions on the Earth's surface. So that doesn't mean they exist as a gaseous form in the conditions where magma is forming underneath the ground, but these would be compounds like carbon dioxide, like oxygen, or could be oxygen, could be water vapor. And we know that these are brought down into deeper depths of the Earth by subducting plates. So little cracks and fractures in the crust on the surface of the ocean have different kinds of dissolved gases in them and water in them that has dissolved gases in it. There's this conveyor belt of the subducting plate that's bringing this material down. And as it gets down to an adequate depth where it's also getting warmer and warmer as it goes, the volatiles lower the melting point of the rock. So depending on the minerals that are within a particular type of rock, they might have a specific melting point of like 800 degrees Celsius that would be required if the rock didn't contain those volatiles, but perhaps the rock can melt at only 650 degrees if that particular mineral can melt at 650 degrees if volatiles are present. So because the volatiles are there, they lower the melting point of the rock and they allow a melt to form in this area on the surface of the subducting plate, even though the areas around it at the same depth that have the same temperature are not forming magma. And then we learned before that that magma bubbles up to the surface and creates these volcanic arcs that are offset from the plate boundaries along these subducting plates. So that's one thing. And here's a diagram of essentially what I was just mentioning. So we have a rock like granite that is more felsic in nature, that has certain minerals like quartz in it and feldspar in it. If it was dry, so not containing these volatiles from a subducting plate, its melting point would actually change with depth, because we said under different pressures, your melting point is actually going to change. But dry granite would have a melting point in between 800 degrees Celsius and then up to over 1,000 degrees Celsius at depth. Whereas when the granite contains volatiles, it actually drops. So as at the surface, it has a melting point that's pretty similar, about 800 degrees Celsius or 750 degrees Celsius. And then that wet granite, or the granite that contains those volatiles, is actually going to be able to melt at even lower temperatures, getting down to something like 650 degrees at greater pressure at depth. So the wet granite, the granite that contains volatiles, is able to melt in some cases at nearly like 200 to 300 degrees Celsius lower temperature. And then this is a melting point curve for dry basalt. So this isn't showing the wet basalt, but basalt is another type of rock that contains more mafic minerals. And so those mafic minerals in general tend to have higher melting and freezing point. So they have to get hotter before they melt, but then they're also going to freeze sooner than rocks that contain more felsic minerals. So the presence of volatiles is one of the things that might contribute to the formation of magma. The next thing is something that's called decompression. So we've mentioned a couple times in here that pressure is something that can influence whether something is able to melt. Temperature isn't the only factor that determines whether a solid becomes a liquid. And so at certain places, particularly along rifting zones or these divergent plate boundaries, what we see is that as the overlying rock starts to slide away from the center point where the divergence or where the rifting is happening, that relieves pressure on the rocks that are below the surface. And so these rocks that are hot, but maybe not quite hot enough to melt, all of a sudden find themselves under lower pressure, and that lower pressure now gives them a little bit more ability to move, to get like looser, right? Which a liquid is like looser than a solid. And so then we'll start to see what's called decompression melting, or a melting process that is facilitated by the reduction in pressure. And then we'll see that magma rise up to the surface to create volcanoes along these rifting zones. And then this is kind of a positive feedback cycle that pushes the rocks out of the way, where the rocks are sliding down the slopes of these kind of volcanic ridges that form. That leads to more decompression melting, and so this process kind of feeds on itself. But a change in pressure is another thing, in addition to the addition of volatiles, the first thing that we talked about, that could kind of tip the balance in the direction of melting. And just like in the case with the introduction of volatiles, you can see that in this diagram at other locations that are covered up with more surface material and therefore under more surface pressure, that are at a similar depth and so therefore would have a similar temperature, are not melting. It's only this area right at the center that has this kind of distinct reduction in pressure. Okay, then the third thing I want to mention is just the addition of heat, so just like extra energy ends up coming into a particular area that can increase the temperature enough to create melting in a certain spot. So the temperature of one particular place below the earth might not be the same temperature as an area nearby at a similar depth. And so in particular, we have this phenomenon, or these structures within the earth that we know as mantle plumes. So these are associated with these hot spots that we talked about before. And basically they bring hot material, including magma, up to the shallow crust. It kind of melts through the shallow crust and then can create these hot spot volcanoes like the Hawaiian volcano chain that we talked about before at the surface. So first of all, I just want to acknowledge that there's still a little bit of not controversy of the fact that we have these hotspots and mantle plumes. We know that they for sure exist, but it's a little bit controversial of exactly like how much melting is happening at depth and exactly what they look like. But we for sure know that there is this material that's coming up in certain spots that's a little bit hotter than the area around it. And as either just the energy itself, the heat travels through more solid material, or if material is melting at depth, that's part of the controversy, exactly when it's melting and where it's melting. But as that travels up to the surface, it is melting other material in its path, and it is creating magma just by the fact that the material is actually hotter than adjacent material. So if you just add enough additional heat, then that's another way that you can get something to melt. Okay, so just to recap, melting occurs deep within the lithosphere where the temperatures are certainly hotter than they are at the surface, but not hot enough. So one of three additional things has to be going on for magma to form. The first thing is there has to be the introduction of volatiles, which can happen along subduction zones. There can be decompression, where the overlying earth material slides away and the lower pressure leads to or allows for melting, lowers the melting point as well. This is what we see in like rifting zones or divergent zones. Or we can have mantle plumes that are bringing extra energy to a specific spot within the Earth's mantle or the Earth's crust that allows an increase in temperature that's adequate to seed melting. So one of these three things is going to happen, and we're going to have different kinds of volcanoes along these different areas where different types of magma are forming. Okay, that's a good stopping point.